Okay, so where we left off was the part about generating electricity. And I'm going to give kind of a simplified overview of generating electricity. In any electricity generating plant, there are two major components. And one of them is the turbine, and that's basically a shaft attached to a coil of wire. And the other is the generator, which provides a magnetic field. And as we would see if we had enough time to go into the electricity section of physics, moving a metal wire through a magnetic field or vice versa creates an electric current. Basically, the magnetic field manages to rip some electrons away from their parent atoms, and those electrons then travel through a wire and can go from one place to another if the wire is attached to something on either end. And so, in other words, that's flows of electrons. You could move the wire through the through the magnetic field, or you could move a magnet through a coil of wires. Either way, it would work. You can actually see that kind of thing in action with some of those flashlights they sell. I used to have one. Unfortunately, it didn't work, so I got rid of it. But the type of flashlight they sometimes still advertise on TV, where you can just sort of shake the flashlight up and suddenly it produces light. Because what you're doing there is, if you look at it, most of them are translucent, so you can see inside basically what's going on. You can see a coil of copper wire around the outside of the flashlight, and the thing that goes thump, thump back and forth when you shake it is a magnet. And so there is a magnet going back and forth over and over again through that coil of wire, and that, in theory anyway, produces an electric current, which can then be stored up by the storage battery that's also inside there, and then you can use that electricity later on when you need light. That works fine in theory. As I said, in practice, I found out it didn't work so well. So, but anyway, that's the theory. The turbine in a power plant is like a long shaft, and it often has something like a fan, or like fan blades on one end of it, and that's so that something can come along and cause the shaft to rotate. And up on the other end of the shaft is a coil of wires, and that coil of wires will be housed in the generator, which has electromagnets all the way around it. So something that comes along and causes the turbine to spin will have the effect of spinning around that coil of wire in the magnetic field, and that produces a flow of electrons. And those electrons that can then be harnessed to go out through the wires and, power the light or the computer or whatever. But that's essentially the idea of how electricity is generated. This is a very simplified view, but actually these are the essential components in just about every electricity generating plant there is. It comes down basically to this. The big difference is that different types of plants use different methods to turn the turbine. And that's really how most power plants differ from each other. How do you turn the turbine? And so basically, we're converting mechanical energy to electrical energy. And we do that in a variety of ways. We do it, of course, mostly by making that turbine spin so that the wire can spin around in the magnetic field. But like I said, how do we make the turbine turn? Well, one of the very common ways that a lot of types of power plants have in common is that oftentimes they will turn the turbine by pumping steam past the blades at the bottom of the turbine. You know, those fan-like blades. And anything that causes those to turn will cause the turbine to turn. And there's a variety of different ways that you can produce this steam. You usually have to have a source of water, so you bring water into the plant from, say, a lake or a river. And steam is produced from water by heat. And then the main difference is, how do you produce the heat? Well, you can burn coal, you can burn natural gas, you can burn oil. There are a few plants here and there that burn petroleum. You can use nuclear fission. So heat from a nuclear reaction can be used to heat water. That's how most nuclear plants work. There is geothermal. That is heat from the earth. Sometimes geothermal can be used in other ways, but sometimes it's used to heat up water. There are also, these are the main ways that you can produce water. You can also turn the turbine directly with things like flowing water, or especially falling water. And that's how they do it at Niagara Falls. There's also wind. That's how wind turbines work. Is essentially the same thing, except it's up at the top of the the tower. Okay, there's also there's also solar power. Solar power uses the photoelectric effect, which was discovered by Albert Einstein in 1905. Well, actually, it wasn't really discovered by him. It was explained by him. It was a phenomenon that was already known. What this means is that sunlight basically transfers some of its energy to the solar cell, which releases electrons. And those electrons can then be funneled through a wire, and there's your electric current. Various materials are more prone to giving up electrons than others are. Unfortunately, the materials most prone to giving up electrons are also fairly rare and fairly toxic. So, so solar is, they're working really hard on developing safer and more common materials that can be used with high efficiency in solar cells. Possible source of energy for the future would be hydrogen. Burning hydrogen can produce a lot of energy in the form of heat. That heat could then be used to heat water, which would turn to steam and which could turn the turbines in a power plant. The only problem is that we currently get most of our hydrogen from steam treatment of hydrocarbons. That, hydrocarbons like oil and natural gas, things like that. And the other product from steam treatment of hydrocarbons is carbon dioxide. And producing less carbon dioxide is the main reason that we want to switch to hydrogen in the first place. So what we have to do is find a more environmentally friendly way to produce hydrogen, which we can then burn. And when you burn hydrogen, it produces nothing but water vapor, no carbon dioxide or other greenhouse gases. So that would be a big step forward. It's possible that we might eventually be able to use solar cells to do electrolysis on water, which splits water into hydrogen and oxygen. And the hydrogen can then be burned as a clean energy source. But solar cells at this point are not really efficient enough to be able to do electrolysis on very large volumes of water very efficiently. So that's something that's still coming in the future, I'm afraid. And let's see, where are we now? That means actually we're at the end of chapter 3. So we can begin chapter 4. We're only a little bit of the ways into this segment of the video, so I'll begin chapter 4 instead of starting a new segment. So chapter 4 is on heat and temperature. It's about, basically heat is related to the idea of thermal energy. And as we mentioned in the last chapter, everything has thermal energy above absolute zero. Which is 0 Kelvin or negative 273 degrees Celsius or negative 459 degrees Fahrenheit. And that means effectively that everything has thermal energy because, as I think I've mentioned before, nobody has ever actually reached absolute zero. Nowhere in the universe is at absolute zero. There are some spots far away from the nearest star, which would be pretty close to absolute zero, but still not absolute zero. Even in the most harsh and extreme conditions in the laboratory, nobody has ever managed to produce absolute zero. They have actually come within, I think, a few millionths of a degree of absolute zero, but they haven't actually gotten there. And they probably never will, because for one thing, getting to absolute zero would require that all motion stop. And that includes motion like vibration of atoms, but also the electrons zipping around the nucleus of atoms would have to stop. And there would have to be no disorder at all in anything at that temperature. So every atom would have to be lined up exactly the same direction in exactly perfect rows with nothing even a little bit out of place. And that's probably never going to actually happen in real life. So we probably never will reach absolute zero. And so in other words, everything has thermal energy. And the amount of absolute energy something has is directly proportional to the absolute temperature. That would be the temperature in kelvins, not in Celsius. And in practice, thermal energy results in the vibration of atoms and molecules. Thermal energy is an internal energy that can be exchanged with the outside world by various means. And those means could include things like radiant energy, that is giving off like infrared radiation, or mechanical energy. For example, friction. And it's important to keep in mind, though, that heat and temperature are not the same thing. They are related. Okay, so temperature is just a measurement of the average kinetic energy of the particles in a substance. And that KE, that kinetic energy, is due to thermal energy. So temperature is sort of a measurement of thermal energy. Okay, so for a given object or sample, as long as the temperature doesn't change, the heat energy actually depends on mass. Because, you know, by heat energy, we're talking about the total amount of thermal energy in an object. And for the same object at, well, say for the same temperature and the same kind of substance, the total thermal energy in the object would vary according to its mass. More mass means more substance, and more substance would mean more total thermal energy. So to look first at temperature in a little more detail before we go on. There are several common temperature scales. They were devised at different times by different people, and they're used in different areas for different purposes. There is, of course, the Fahrenheit system. That dates to 1724. This is the English unit of temperature. Kind of ironic, since Fahrenheit is about as German a name as you can imagine, that it's the English system. It was developed by Daniel Gabriel Fahrenheit, a German physicist, and he's the guy who invented the mercury thermometer a few years earlier. And he set 0 degrees as the freezing point of seawater, and 100 degrees Fahrenheit was the human body temperature. And he was a little off on both, actually. 0 degrees would be the freezing point of really concentrated salt water. So basically not water from, like the Atlantic or Pacific Oceans, but maybe water from the Dead Sea or the Great Salt Lake might have a freezing point of 0 degrees. And also, of course, obviously on the 100 degrees, he was a little high on the human body temperature. Close, but no cigar. There's Celsius. Or centigrade, as it's sometimes called. This was invented by a Swedish astronomer, actually, by the name of Anders Celsius, and it was devised in 1742. So we tend to think, at least in this country, we tend to think of Celsius as kind of like the new temperature scale because we're not used to it. But actually, it's almost as old as Fahrenheit. This is the metric unit of temperature. It's based on a scale of 100. And it's set 0 degrees Celsius as the freezing point of water, and 100 degrees Celsius as the boiling point of water. And both of those are correct, as long as you're talking about pure water. Tap water might have slightly different values from this because tap water's got stuff in it. So it's not pure water. But if you have like distilled water, it would follow these values. Although actually atmospheric pressure can affect boiling point also. So if you're at average atmospheric pressure at sea level, then the boiling point of pure water would be 100 Celsius. If you've got impure water, or if you're at a higher pressure or lower pressure, then that temperature could be different. This is more compatible, of course, with the metric system because it's based on factors of 10, or in this case, factors of 10 times 10. There's another one, though, and that is the Kelvin scale of temperature. This was developed by Lord Kelvin in 1854, actually, a long time ago. This is the SI unit for temperature. That is the temperature that's used in chemistry and physics because it's an absolute temperature scale. sorry. Yeah. And by absolute temperature scale, what I mean is that 0 means nothing. No thermal energy at all. That's not true for Celsius or Fahrenheit. At 0 degrees Celsius or 0 degrees Fahrenheit, you still have quite a bit of thermal energy. The particles in a substance are still vibrating fairly quickly. And you can actually go below 0 on those temperature scales, and the particles will still be vibrating for quite a ways below 0. On the Kelvin temperature scale, 0 is absolute 0, and again, that means no thermal energy at all. It means that if you were to reach 0 Kelvin, and technically we don't say 0 degrees Kelvin, we just say 0 Kelvin. 0 Kelvin means no thermal energy at all, which means no vibrations at all. And you can never go below 0 on the Kelvin scale. Zero is the lowest you can go. 0 means nothing, and you can't go any lower than that. And what that does is it puts temperature measuring on the same basis that we use for measuring everything else. If you think about, say, length or volume or mass, measurements like that, all of the temperature scales we use for those scales of temperature, for those measurements, are absolute temperature scales. If you think of a length, 0 inches is nothing, no length at all, and you can't have a negative length. And 0 feet or 0 inches would be the same as 0 feet, which is the same as 0 meters, which all mean no length at all. That's not the same in temperature. 0 Kelvin is not the same as 0 Celsius, and 0 Celsius is not the same as 0 Fahrenheit. So that's why we stick with the one that's absolute. If you're thinking of volumes, 0 volume means nothing, and you can't have negative volumes. 0 milliliters is the same as 0 fluid ounces, which is the same as 0 gallons, and so on. Those are all absolute measuring scales. But again, temperature is not unless you're using Kelvin. Okay. So absolute 0 would mean no molecular vibrations. And perfect order of molecular alignment. Actually, there is one more temperature scale that I'll just mention, and that is the Rankine temperature scale. Interestingly enough, the Rankine temperature scale is actually newer than Kelvin, even though Rankine is based on Fahrenheit and Kelvin is based on Celsius. This is the English unit for absolute temperature. And so this is the absolute temperature scale based on Fahrenheit. In the case of Kelvin, in the case of Kelvin, 0 Kelvin is absolute 0. That's negative 273 Celsius. 0 Rankine is also absolute 0. So actually 0 Rankine is negative 273 Celsius also. But the way it was first calculated is according to the Fahrenheit scale. and that would be minus 400 and, well, negative 459.67. So I'll call that negative 460 degrees Fahrenheit. And that means also that by transference, of course, that negative 460 Fahrenheit is the same as negative 273 Celsius, I mean. Okay, so we're at 30 minutes. When I come back in just a moment, I will do a comparison of some common temperatures in the different temperature systems, and we'll see how to convert from one system to another. But we'll see in a moment.